All right, let's go ahead and get started. From what I heard, y'all finished 3.5. So I don't want to go into it into more detail than we have to, but I did want to give you all the opportunity to ask me any questions I didn't know you did on Monday. Go ahead.
I only want to know, to what extent should we memorize the trig derivatives?
The inverse trig derivatives?
Yeah.
So I'll build up one of these, but in general, I believe if you can, I mean, the less you have to memorize, the better, especially for math. So here's the way that I would have done this with y'all. So take the derivative of inverse sine of x. I'm going to instead write this as x equals the sine of y. And then from there, you can take a derivative of that implicitly, right? So if I differentiate both sides with respect to x, I get 1 equals cosine of y dy dx. Which then means I have dy dx equals 1 over cosine y. Is this kind of what he went through with you? Or did he not develop it this way?
It's not that way.
Okay, so the derivative of inverse sine of x is 1 over the square root of 1 minus x squared. That is the derivative. This is how I like to show where it comes from. If you can commit what the derivative of all those inverse, of at least the 3 primary inverse trig functions are, if you got those memorized and you're faithful, you have faith in that, awesome. If you're not, I mean, you can kind of rebuild it this way if you absolutely have to. If a little bit of test anxiety kicks in and you just lose it. So I don't want to leave this as 1 over cosine y because I got y involved there. So here's what I do know. I'm going to build a triangle here. I know that y is an angle, or I can call it an angle because I'm taking the sine of it, right? You okay with that? If the sine of that angle is x, then I can say this. The opposite side I can call x, and the hypotenuse I can call 1. Because the sine of that angle is x, or x over 1. I know those two sides have to be united in that ratio. Can I say anything about the base of that triangle now? What kind of triangle is this? It's a right triangle, right? So I can say a squared plus x squared equals 1. A squared equals 1 minus x squared. A equals the square root of 1 minus x squared. It's a length, so does it make sense to say plus or minus? I'll just call it positive. So Pythagorean theorem lets me say that about what A is. So now, why go through all that trouble? What is the cosine of y in that triangle that I now know all the sides of? Nope, sine is x over 1. So what's cosine of that angle? A over 1, right? Or what I found for A, which is 1 minus radical 1 minus x squared. So that's why this derivative is this thing. So I'm not going to do the other two in this way. But if you want to do it to kind of convince yourself of what those derivatives are, I recommend it. You can follow a pretty similar process to this. But having said that, at the end of the day, you got to know those 3 inverse trig relationships and how to take derivatives of them. Anything else about Monday stuff? If not, I will move on. Okay, so let's talk about Section 3.7. All right, so last section of the chapter. So just looking forward, this is where we're going to end before spring break. So this is the last section of the chapter. It's also the last section to be covered on the second test. The second test happens on March 16th, which is the Wednesday after we all come back. I will not be going over new stuff on Monday. I will basically Monday's going to be like a Q&A review type day. So I will not bring things in. I won't have anything concrete planned. It's really your time to ask me questions. So any questions about what the next 2.5 weeks or so look like? Or I guess 1.5 weeks. Okay. All right, so let's get into this. We're talking about something called L'Hopital's rule, and indeterminate forms are really what it is used for. So let's kind of motivate that with these 3 examples. Can you find any of these limits with the tools you have now? Yeah. Which one or which ones? The first one. The first one? What's the limit of that first one? So that's x going to infinity, right? What's going to happen to the numerator as x goes to infinity? How about 5 to the x? So what's the limit? Can't really say 1. We don't know for sure, right? So again, thinking back way back to the start of the semester about limit laws, I can't really break these things down if the individual limits don't exist. If the limit of the numerator is infinity and the limit of the denominator is infinity, neither one of those limits exists. I can't just divide infinity by infinity. How about that middle one? So are any of these things available to you right now? So I agree with you about the first and last one. Thing I want to remind you about is this. We can do things like this, right? So that limit should be 2, right? So after I make that simplification, now I would get to a form where I can substitute 1 for x and enter that. But I believe right now the top one is something you don't have access to yet. How about this one? What's going to happen is to natural log of x as x goes to infinity. If a number is getting larger and larger, and I take natural logs of those things, what happens to those output values? Not, I mean, they keep growing. I mean, this is one thing we talked about on Friday was this curve here. If this is x and this is natural log of x, then you have this relationship here where as x gets bigger, y always gets bigger, but that rate at which it grows will always be decreasing. But it never stops, it never becomes negative, it never decreases. So I can make the natural log of a number as large as I want. How about the denominator? What happens to x plus 7 as x goes to infinity? That goes to infinity as well, right? So these are kind of things that, this is what L'Hopital's rule is built for, these things that we can't really interpret yet. So there's a whole bunch of indeterminate forms, and L'Hopital's rule is useful for 2 of them. So let's just say I have this limit. The limit is x approaches some number, or it even could be infinity, of f of x over g of x. So 2 functions, one divided by the other. That's not necessarily a rational function because I'm not putting any requirements on f or g. They can be any functions of x. But if one of these two things is true, if either both of those limits are 0 or both of those limits are infinite, this is what's called an indeterminate form. There is, so 0 divided by 0, there is no universally agreed upon answer for what 0 divided by 0 is. Same with infinity over infinity. Seems like it should be 1, I guess. But it's not, that's not agreed upon. These are indeterminate forms. We don't know these results. So this is the kind of thing that L'Hopital's rule is used for, these and nothing else. If we're looking at these limits where the limit at first glance is either 0 over 0 or infinity over infinity, then here's what L'Hopital's rule allows us to say about the limit. If you have one of those indeterminate forms, then the limit of that f of x over g of x is equal to the limit of f prime of x over g prime of x, as long as that exists. So let's pull up one of the examples that we had just a bit ago, which was the limit as x approaches infinity of e to the x over 5 to the x. It might have been reversed, but I don't remember. That was something we couldn't quite agree on, right? Because it comes out to something like infinity over infinity. So now what can we do to find that limit based on this rule I'm showing you here? Yep. So, and I can take, and not quotient rule, you're just taking the derivatives independently. What's the derivative of e to the x? E to the x. What's the derivative of 5 to the x?
5 to the x natural log of 5.
5 to the x natural log of 5. This is a bad example. I'm gonna abort on this one. So because these are exponential functions, those e to the x will never go away. But the bottom one I showed you, we can definitely look at.
Does it only work with indeterminate limits, or any limit that can be found?
No, only so it's not even all indeterminate forms, it's really just those two. So by the end of this, I'm going to show you lots of indeterminate forms. It only works with these, like these two.
0 to 0.
Yeah. Like for example, we're going to see like 1 to the power of infinity, which is not a thing that can handle. You can kind of rework it to fit that mold, but okay, so this thing right here, does this fit the L'Hopital's rule criteria?
Yes.
Okay, I have an infinity over infinity indeterminate form, which means I can use L'Hopital's rule. What's the derivative of the numerator?
1 over x.
It's 1 over x. What's the derivative of the denominator?
1.
Okay. Is this a limit that we can get our hands on?
Yeah.
What's that limit? 0. So not obvious the first time we looked at it, but now it's pretty simple to get to. That limit is 0. Unless here's another way to think about it. Let's think about the derivative of x plus 7. You said that was 1, right? That's a straight line. That has a constant rate of change, 1 for all values of x. I just showed you a graph of natural log of x. The larger x gets, the lower the rate of change gets, right? So basically you have a function where, yeah, they both go to infinity, but the denominator grows faster. So you're going to get a limit that trends towards something. It's not always going to be 0, but it's probably going to exist if the thing you're dividing by grows faster than the numerator. Does that make sense? Okay. Let's look at some more examples. This one, can I skip this one? Is this going to be any different from the one I just had y'all do?
Yeah, same thing.
Yeah, so this is going to have the same limit as natural log of x over x plus 7. So I'll just say here, that equals 0. The note that you can go back and try that one, but it's very similar to the one we just looked at. All right, sine of t over t. So what's the first thing we really should look at to evaluate this limit? I think that's not the first thing we should look at. I need to make sure that L'Hopital's rule is even available to me. So let's make sure that that is an indeterminate form. Do we think it is?
Yep.
Why?
Sine of 0 is 0 and t is 0.
Yep. So this is a 0 over 0 situation. So then what is this limit equal to? Cosine of t over 1. So yeah, derivative of sine of t is cosine t. Derivative of t is 1. Is that a limit I can get to? What is that limit?
Is that one nonsense?
I don't know. You can.
No, then it's 1.
It's 1. Why is it equal to 1?
Because cosine of 0 is 1 divided by 1.
Yep. And just one thing I'll remind you of. Something we said a while ago, maybe you forgot. All trig functions are continuous if they're defined. And cosine is defined everywhere, so. The limit is equal to cosine of 0. How we doing? All right. What do we need to do? Look at the individual limits. So let's write that out. What is the limit as x approaches 1 of arctangent x minus pi over 4? What is the arctangent of 1? It's hard to think in inverse trig functions. So instead of asking yourself, what's the arctangent of 1? What's a similar corresponding question you could ask? Was that?
It's not the inverse, like
Yeah.
the inverse of tan 1. Like
Well, that's what arctangent is. What's that? Oh, yeah. Was that, so that's another thing to bring up. Inverse tangent is not the same thing as cotangent. Garrett?
arctangent of this 1 pi over.
Yes, it is. So let's talk about why. So arctangent of 1 is pi over 4. So think about how inverse functions behave. What's a corresponding statement I could make to that? Arctangent of 1 equals pi over 4. Right, tangent of pi over 4. And if you don't recognize it, pi over 4 is 45 degrees, which has a tangent value of 1. So this limit is 0, right? So far so good. What needs to be true about the denominator limit? Do we believe it's 0?
Yeah.
Yeah. So yeah, the x minus 1, I can evaluate that at x equals 1, I get 0. So that means we have L'Hopital's rule available to us. So the limit above is equal to something over 1. What is the something? Garrett?
1 over 1 plus x.
We agree with that? 1 over 1 plus x squared?
Yeah.
All right. We can get rid of that denominator. Is this something we can evaluate? What is it? 1/2. What kind of function is that you can just assume continuity? I'm guessing you just plugged in 1 to get 1/2, right? So can't always do that. We can with this kind of function because it is what? It's not a polynomial, technically. It's a polynomial divided by a polynomial, which are called, there you go, yeah. But that's why we can do that. Any questions about that one? All right. What now? Okay, so let's look at the limit as x approaches negative infinity of x squared. What is that? Infinity? The numerator?
Yeah.
I agree with infinity. So as x becomes very, so x is going to go far left, right? What happens if you take a a negative number with a very large magnitude and square it? If it goes positive and its magnitude becomes larger. So it's going to keep growing. This other one might not be very clear at all. So the limit as x approaches negative infinity of e to the negative x. Here, vote for infinity. Why?
No matter what the negative number is, if you multiply the negative one, it's a positive, then it's just e to a positive exponent.
That's perfect. Yeah. So bottom line here, you're raising e to larger and larger positive numbers. This limit is infinity, so we are good. So from here, I can say the limit I care about is equal to some other limit. What is that limit?
2x over, is it e to the negative x?
Is what?
The derivative of e to the negative x is.
Or would it be negative?
So you're saying negative e to the x?
No, I said that. He said, is it just the same thing? E to the negative.
Those are both close, but neither is totally correct. So let's think about it this way. Back to my block diagrams. What's the first thing that happens to x? It gets multiplied by -1. And then it gets raised, or it becomes the power to which e is raised. Okay, so now you got not the most complicated composite function in the world, but really should be thinking about chain rule. What's the derivative of e raised to something? It is e raised to that same thing, right? That doesn't get altered. But what's the derivative of that other function? -1. So basically, I would call this function f of x equals -x. And this is f of x equals e to the x. So yeah, that e to the x, or I guess I should call one of them something other than f. So the derivative of your, like your fundamental exponential function, that is self-differentiable. Comes e to the x, then the other one has a constant derivative of -1. All right, so what do we do with that limit?
So the top is gonna be negative, no matter, like,
Did I say x goes to infinity?
negative,
Yeah, that's a mistake. So the top is going to go to negative infinity, right? What is the denominator going to go to?
also negative.
So now what do we do? I mean, that's not, I can't really say that's the limit, right?
You do it again.
I can do it again. So I don't care how I got to the indeterminate form. So I did the L'Hopital's rule and I got, because I had the indeterminate form of infinity over infinity. Then I did it again. Or I took derivatives and I found an indeterminate form of infinity over infinity. So I mean, nothing about that rule that says I have to stop at one iteration. So now, what new limit am I looking at? Yep. Can I use L'Hopital's rule again?
No.
No, this is no longer indeterminate. So I can't use L'Hopital's rule, but I don't really care because now I have access to that limit. What happens to 2 as x gets very large? You still stays 2. What happens to e to the negative infinity or e to the negative x as x goes towards negative infinity? So the denominator is getting very, very large, right? So then that limit is 0. Because the limit as x approaches negative infinity of e to the negative infinity is how are we doing? Okay. How about this sine theta over 1 minus cosine theta? What do you want to do?
Sorry, what's the limit? Theta to,
Yeah, what does that mean?
you're like, what's it going to? I can't even see it.
Oh, it says theta, right arrow, pi raised to the, like, with a negative superscript. So are you asking what that meant or just like literally what it said?
I just couldn't, yeah.
Oh, okay, I got you.
What does that mean? Oh, it's that.
Yeah, so what does that mean?
Negative 1.
What's that?
I to the negative 1.
No, so it's not raised to the negative 1, it's just, that's just a negative sign like it's a superscript.
Going from the left.
Yeah, so as I approach pi from the left, right? So usually I have to approach my base point from like above and below. This time I only care about theta values that are less than pi. So from the left, from below. All right, so what do I do? Oh, and we're way beyond that, the table of value stuff. We have all kinds of more high-tech limit techniques now. We just did L'Hopital's rule, right? Let's do it, right? You okay with this? What's the cosine of pi? It's not 1. It's -1. Here's your unit circle. The cosine of an angle gives you the x coordinate on the unit circle, right? Pi is putting you on the negative side of the x-axis. It should be -1.
Is there a way just like little thing? Is there a way just like calculate with that if you know like a certain pi value, you just input it to cosine, like mathematically just find the value instead of memorizing the unit circle?
I'm not, so to be clear, I don't have the unit circle memorized. I think I don't think that's a worthwhile thing to do. But what I do know is, and that's the kind of why I draw this out for you. I know that this point right here is cosine theta sine theta, right? So if you remember that, that's really what sine and cosine are. They are just the x and y coordinates, respectively, of whatever the point is that that angle projects onto the circle. You can get all your sine and cosine values. If you, I mean, you probably have to draw a picture and kind of work it out, but yeah, I think if you look at the unit circle and all the 16 different angles on it and try to memorize them all, that's not worthwhile. Do you have a question?
Yeah, sorry, so we know originally that we could use L'Hopital's rule because it's 0 over 0, right?
Did we even look at that?
No, we just skip right to the,
Should we look at it?
do we have to? Or is it-
We always have to. So L'Hopital's rule only works for two indeterminate forms, 0 over 0 or infinity over infinity. So we didn't even look at that. So should we look at it now?
Yeah.
What's the limit of the numerator? Yeah, sine theta. I mean, these both better exist because sine and cosine always exist. So what is the limit as theta approaches pi of sine? That one's 0. So that's a good sign. What's the limit as theta approaches pi of 1 minus cosine theta? What is that? What's that?
Also there, you have 1 minus 1 over 1.
What is the cosine of pi? It's not 1.
I know we did negative 1.
Yeah.
Oh, then it's negative 2.
So it's 2.
So am I even allowed to touch L'Hopital's rule for this one? No. So this is, threw this in here to show you, you really need to make sure that before you go wasting a bunch of time with L'Hopital's rule, I mean, if you do not have an indeterminate form, it can tell you bad information. So from here, now let's say we were working with this. This is -1 over, that goes to 0, right? This would look very much like a limit that doesn't exist, like, yeah, like something, it would be negative infinity. Which if you just take L'Hopital's rule and the information it gives you, it's going to give you bad information. But what is this limit really? The numerator goes to 0, the denominator goes to 2.
Yeah.
It's just 0. So the limit as theta goes to pi from the left is yeah, those indeterminate forms really have to make sure we have one of those. Go ahead.
On the second line, how is the denominator sine theta?
Because the derivative of cosine is negative sine, right?
Yes.
And there's a negative coefficient on cosine to begin with.
Shouldn't that be 1 plus sine theta?
No, the derivative, what's the derivative of 1?
Oh,
Yeah, it's a constant, so it vanishes. Anything else? Okay. All right. Can I use L'Hopital's rule here?
You have to rewrite the function
So why can I not even think about it right now?
because it's not even a fraction.
I do not have anything divided by anything else. So it would seem like at this state, like L'Hopital's rule is not something I can use. But Solomon, you had an idea. So let's think about this. Individually, what is the limit as x approaches infinity of e to the negative x? Not negative infinity. It's 0. Because basically that's 1 over e to the x, right? And 1 divided by something that's growing without bound will get smaller and smaller towards 0. What is the limit as x approaches infinity of radical x. Well, what's root infinity? I mean, it keeps getting larger and larger. So the square root function is going to look similar, because I'm not very accurate, to the way the natural log function looks, but this is not the natural log function, but the similarities they share that are important is that the square root function is everywhere increasing, but its derivative is everywhere decreasing. So it always increases, but the rate is always diminishing. But you can still make it as large as you want. So this is another indeterminate form. This 0 times infinity thing, which can't really agree on. It's like, well, it's a number that it can get as large as, it can get arbitrarily large. But if I have 0 of it, what do I really have? So that is an indeterminate form, but that is not one of the indeterminate forms that L'Hopital's rule can deal with. But can we rewrite this thing to put it in a language that L'Hopital's rule can deal with? Yeah. We can put e to the positive x as the denominator. So this is the same thing as radical x over e to the x. Is this a form that L'Hopital's rule can deal with? Yep. So yeah, as x gets very, very large, radical x will get very, very large, and e to the x will get very, very large. Which one of those is going to be growing faster? Square root or e to the x? So if the denominator is growing faster, what do you think about that limit? Should be getting closer to 0. So let's see if that shakes out. But do we agree that L'Hopital's rule is okay now? All right. So by L'Hopital's rule, this equals the limit as x approaches infinity of what? So denominator is 1 over 2 radical x over?
Yes. Exactly.
All right. So how can we think about this limit?
The denominator is always, I mean, the numerator is always getting smaller and the denominator is getting bigger.
Right. So now we have this form. Basically, you have 0 over infinity. Is that an indeterminate form? Nope. So basically what you have here is this, and I'll write this out again. The limit as x approaches infinity of 1 over 2 radical x is 0. The limit as x approaches infinity of e to the x is infinity. So you have a number that's trending towards 0 divided by a number that's increasing without bounds. So this limit right here is, therefore, limit as x goes to infinity of go ahead.
When you rewrote the equation to when you rewrote the equation to the top, would it have been the same if you just put e to the negative x over x to the 1/2?
X to the negative 1/2?
Yeah.
Yeah, so I don't think we're going to go through it, but yeah, another perfectly good rewrite of this is e to the negative x over, for now, I'll draw it like this.
That might still give you the same answer.
Let's think about it. So will L'Hopital's rule work? So here's the thing. If this limit exists, it better be the same as what we just found. I mean, all valid methods will get to the same place. What is your new numerator going to go to as x gets very, very big? 0. How about the denominator? I think also 0, right? So L'Hopital's rule is available to you. And We'll go ahead and leave it there, but I'll promise you that if you do it right, the limit is going to be zero. Good question. So, and that's just highlights that the way I rewrote it is not the way to rewrite it. Anything else? All right. Is this something we can use with L'Hopital's rule? Don't really have a function divided by another function, right? I mean, it's hard to say what those things are without doing some work. So let's look at it this way. What happens to 1 over x as x goes to 0 from the right? We can say more than that. So yes, the limit does not exist, but we can be a little more specific. I'm dividing 1 by numbers that are getting smaller and smaller and smaller, but they're always positive. That goes to infinity, right? What about this other one? The limit is x goes to 0 from the right of 1 over 1 minus e to the negative x. What's that e to the negative x term going to go toward? Not 0. So the power on e is going to go towards 0, right? So the power that something is raised to is turning towards 0. What is that overall term going to turn towards? Go towards 1, right? Anything raised to the power of 0 is 1. So then you have 1 over 1 minus 1. That goes towards infinity, right? So here's another indeterminate form. Infinity minus infinity. Which you might be tempted to call that 0, but that's it for sure. So this is indeterminate form, but it's not one that L'Hopital's rule can deal with. So we need to think about how we can talk about this function in a way that L'Hopital's rule can handle it. Garrett?
E to the negative x, or negative e to that negative x on top.
So the problem there is the fact that it's added to 1. So I can't just move that up on its own. I have 2 fractions. I'll say added together, but same idea. Isabel, do you have your hand up?
Make the denominators one, the same.
Okay. So if I can find a common denominator, what's a good common denominator for these 2 fractions? What's that? Yeah, really, they don't really have anything in common, so I really need to just multiply them by each other. So my common denominator is going to be x times 1 minus e to the negative x. What will the numerator look like if I do that? From the first fraction, the 1 over x, the contribution is going to be 1 minus e to the negative x, right? What will the contribution be from the other one? Minus x. So this thing, if I let x go towards 0 here, what's going to happen to my numerator? I'm going to have 1 minus, okay, the very last term is easy to think about, right? That'll go towards 0. What happens to e to the negative x? Goes towards 1. So I believe my numerator So as x goes to 0 from the right, this goes towards 0 over. What is the denominator going to be? Also 0, right? I mean, I don't really care what's going on in parentheses. If x goes towards 0, it's going to multiply by that bracket. So is L'Hopital's rule now available to me? Absolutely. So now I can look at this limit. The limit as x approaches 0 from the right of what new function?
One minus e to the negative x minus x.
Oh, so I guess I should be more clear. Yeah, so that's what I was getting at, but I should really be complete here. So this, by virtue of L'Hopital, is equal to, what is the derivative of our numerator? What was that one more time? E to the negative x minus 1 over what? I'm going to extend this. I think we'll need it. What do we have to do with that denominator? Got to use the product rule.
Isn't it just gonna be one minus e to the negative x?
I don't think so. Let's see.
Because if you,
Would that negative go away? One minus e to the negative x. Well, the negative, I'll let you go.
Well, we got to use product rule here. So
I'm
we're,
talking about the so you took the derivative of 1 minus e to the negative x minus x. Right?
yep. So the 1 vanishes.
So the 1 vanishes. What is the negative on the e to the negative x?
How long ago was that example that we did? The short answer was it a while? I mean, I think we all could use the refresher. But basically the short answer is chain rule.
Oh shoot, yeah, that's right.
So yeah, basically x is getting negated, getting multiplied by -1, and then it's being used as that exponent. So basically the derivative of e to the negative x is e to the negative x times the derivative of the exponent. And that's true for anytime you're going to take a derivative of an exponential function. If it was e to the x to the 4th, that derivative would be e to the x to the 4th times the derivative of x to the 4th. Good question. I'm glad you. No, don't be sorry. I'm glad you asked it. All right. All right. So we got to use product rule to handle the denominator. So the derivative of x is 1 times 1 minus e to the negative x plus x times the derivative of the inside of the bracket, which is e to the negative x. All right, what's going to happen here is x goes towards 0. So the numerator is going to go towards what? 0. How about the denominator? So this is going to be 1, right? This is going to go towards 1 as well, right? So I think the whole thing goes to 0 over 0. So what does that mean? You can do it again, right? Not today though. So we'll pick that one up on Friday, but yeah, we've gotten to a place where we can do L'Hopital's rule one more time. Isabel?
Could you explain 0 to 1 again?
Yeah, so
From the chapter, we get the limit of 0, and that's what I think is very complex.
okay, so for this one here, you're just the denominator is telling me.
Yeah.
Okay. So as x goes towards 0, this term is going to be 1, right?
Sorry, I feel like I'm actually like.
Yeah, and oh yeah. So basically, e raised to the power of 0.
Mhm.
So 1 minus 1 is 0, and then really since this x is going to 0, this
Yeah.
whole thing will go to 0. So yeah, we're level on the indeterminate or another good function for L'Hopital's rule that we can pick up on Friday. All right, I'll see y'all then.